Hello everyone, my name is Sarah. I'm currently doing my internship with the Start Tech Academy, and in this video I will be explaining the tasks that I performed explaining the tasks through that I performed using machine learning to determine linear regression. So the first thing that I will do is to look at our problem statement. And in this this machine learning project, I was to create a linear regression model in Python to predict the CTC or salary of new hires from the data provided. And then we were given two data sets, being the trained data set and the test data set. My task was to understand the data, transform categorical variables to numerical variables, apply linear regression to predict the CTC, and evaluate the result of the analysis. So we're given two Excel data files to help with this assignment. So I will start with this. Like I've said, from my screen, you can see the first thing being I had to put a title so that it be easy for anyone, for us to understand. We create a linear regression model in Python to predict the CTC salary of new hires from data provided. Then what is CTC? CTC, also known as cost to company, refers to the cost incurred by the company in a year for employing a staff member in the organization. That is, it takes into consideration all the additional benefits that an employee in a company receives apart from their salary. So we're trying to predict the CTC for the new hires as the new set of people that the company is willing to hire into its organization. So the first thing we will do is we will import our libraries. We will import pandas. I've already done I've written most of my queries. So the only thing we're going to do is to just run through them. So we import pandas as PD, we import NumPy, we import Seaborn, SNS, and then we import the matplotlib.pyplot because we want to use it to plot graphs. We use the Seaborn for machine learning and then NumPy and pandas for the other tasks. So I will run this first. So I'm done. The next thing is to import the trained data set. We're importing the trained data set because we want to use the trained data set. We want to use the trained data set to train the model before we now test it. So we import the trained data set and use it to train the model. So I give it a variable name of trained data, and then use PD to read in my file. This is my file here. I'm skipping the first two rows because I want my column header to be on the first row, and then I am assigning define data to train data, meaning I want the train data to also be the same thing as define data. So I will run this, and then I'm done. Oh yes, the same file not found because I probably moved my Excel file from where it was. Okay, so my I've brought back my data set so that they can be in the same directory. So I will run it again and then that's gone. Then I need to clean the train data set. I need to clean it. Let me open it so that we can see. Let me run it so that we can see why we need to clean it. Let's look. Yes, so this is the reason why we need to clean it. We have two separate serial numbers. We have the serial number that came with the data set, and then we have normal indexing from pandas. So we need to remove this. We need to remove one. So that's why we're cleaning it. So I use this code refine data dot drop. Let me refine data here so that we'll know that it's the same thing that we're talking about. We'll see it's the same thing. So I use refine data dot drop. We're dropping the serial number that came with the data set. We're dropping that in axis 1 and in place 2. Then when we run this, it will not give us anything because I didn't specify any listing. And then I also want to change this CTC. I want to change it to this. I want it to carry the same data type to the previous CTC. So I applied my numpy integer 64 to find data on the CTC variable. So when I run this, it should give me the same data type. We'll find that out when we get the info. When we get the info for the data set, which is the next phase. So we're getting the information about the trained data set. First of all, we find data dot head, that is to get the first 5 rows, do tail to get the bottom 5 rows. Then we find data dot info to get the details of all the columns represented in the data set. And as you can see, we have 7. We have college, we have role, we have city type, previous CTC, previous job changes, graduation experience in month CTC. All of them non-null. There's no null count, no not variable among them. Then we find data to describe our data set, our training data set. We want to see the count, the mean, the standard deviation, the minimum, the upper, the quarters, different quarters, and then the maximum, the max of the data set. And as you can see, for each column, it's all stated here. Then we'll go to the next task, which is to turn categorical variable into numerical variable. Turn the categorical variable into numerical variable. I want to get the info for this so that we can, so I'll make sure that our CTC and previous CTC are having the same data type. Okay, Okay, let's just leave it there. So we have to turn categorical variable into numerical variable. The first thing we'll do is we need to find the unique values that are associated with these columns. To print the find data, we are looking for the unique value associated with college that's unique value associated with role that's unique, and the unique value associated with city type. Hence the reason for the dot unique after each row and after each column. And then when we run this, we get under the college, we have different categories. These are the unique categories. We have tier 1, tier 2, tier 3. Under rows, we have manager and executive. Under city type, we have non-metro and metro. So we then use the compact feature and use the pd.getDummies to turn these variables, college, role, and city type, being categorical variables into numerical variables. So use the find data is equals to pd.concat, the find data being data set, pandas.getDummies, put in the find data set, variable college axis 1. We do that for row, and then we do that for city type, and then they run it. Then to find out if what we've done actually works, we run it again. And when we run it again, we can see that all the different categories under this thing have been split into separate columns. Different categories under college split into different columns. Categories under road are split into different columns, and categories under city are splitted into different columns, and they all follow the one O this thing, because that's because of follow the one O odd method, method, meaning that for this one now, since the manager does not belong to either a tier 2 or a tier 3, all it will be recorded as 0. Since it's not an executive, it will be recorded as 0 for him. Since the manager will be recorded as 1, and then like that continuously. Then we need to determine the correlation between the variable CTC, that is the correlation between the variable CTC and its correlation to other variables. That is, we want to determine the correlation of CTC to other variables. So we find the data dot call into bracket CTC, because we want to use CTC. We want to see how it correlates with other variables. And this is the figure that we got. Previous CTC, you see, previous job changes, the experience in months. CTC. We are doing this so that we can know which of these variables is actually closest to CTC. That is, so which of these variables can we use to work with CTC to predict the new CTC for the new people that they are hiring. So that's what we did this correlation here. Then we will now import in, let me run this, I don't run this. Then we import in plot peer plot using C1 library to show the relationship and distribution among all the variables. We run it. I set my peer plot style to dark grid. That's why you see all this dark thing. And then I use the SNS the peer plot, use the train data. These are the variables that we're trying to show relationships. So these are the variables that we're trying to show the relation and distribution among them. Previous CTC, previous job changes, graduation mark, experience in months, and CTC. When we run this, you get a peer plot showing the different relationships and different distribution between these 5 variables. We have previous CTC, previous job, graduation, experience in more CTC, previous like that, different relationship and distribution amongst them in the data set, in the trained data set. So now we will now look at the distribution of each variable in relation to CTC. This one will be distribution of each variable in relation, like just like a general show of the relationship and distribution amongst all of them. Now we're going to look at them individually and how they relate with the CTC. We're looking at CTC because that's what we're going to use to predict the new CTC for the new hires that are coming in. So we need to know how do all these variables, how are they distributed in relation to the CTC. So we use the SNS KD plots, and then we plot college based in, we are doing it, we are entering it 3 times because there are 3 tiers. Then like that is equals to tier 1 CTC. For the first graph, we want a shade to be green. We want label to carry tier 1, and that's that. The same thing goes for the second one. We want the shade to be purple, color to be purple. The third, we want the color to be data blur, and these are the different colors. These colors represent the different tiers. As you see, we assign the green to tier 1, the purple to tier 2, and data blur to tier 3. So then we do PLT the legend and PLT show. And when we run this, we get this chart showing the density of distribution for the different tiers of college in relation to CTC. From here we can see that the tier 3 had the highest density. And then followed by tier 1, the highest density. We also do the same thing for the KD plot, the variable role, using the manager and executive categories. We assign different colors to them, and then we run it. When we find out that the executive, they have more density, is much higher density, and higher than, no, there's a much more higher density for the executive when in relation to CTC compared to the managers. Look at the visuals for the old CTC and for the previous CTC and the current one. You can see that the bulk of the CTC in current one is between the 50,000, 60,000 benchmark. When compared, that's for the previous one, and then the current one, the density is mostly spread between 6,000 to, let's say, 8,000 benchmark. Any other value higher than that, the density drops. So we'll also use, that's that about that. We then try and also plot the college, different college in correlation with their CTC value. And when we run that, we are using the bar chart. You can see from here that the tier 3 has more density in comparison with the other 2 tiers. Which is the same thing with what we have here. But this time around, we're using the bar chart. I also tried using the bar chart too with row 2, and As you can see, managers they have a higher density when compared with that of the executive. Density is between the slightly above the 2000 CTC level. Then I now use the box plots in order to show the correlation between the CT type and the CTC value. I'm using the box plots, and then from this box plot we can see that about, let's say, 25% or thereabout of the density in non-metro falls below the 7,000 benchmark, from 7,000 to about, let's say, 5,005 or so benchmark. And then there are also has higher outliers when compared with the metro. The metro has bulk of about 25% of the metro fall between 7.5 and the same thing, 6,005 benchmark with a outlier level of more than 12,000 CTC value. So that is that about that. Then I now tried to see the linear relationship between the CTCs and some variables, key variables. And the first one is the linear relationship between the previous CTC and the current CTC. And I'm using the LM plot chart type. In the LM plot chart type, I assigned my previous CTC to my X axis and then the CTC to my Y axis. Then using fit red true because I want the regression line to show. So by the time I run this, we can see from our chart that there is like a positive correlation between the current CTC and previous CTC. You can see as the previous CTC value is increasing, the current CTC value is also increasing. So as such, there is actually a positive linear relationship between the CTC and previous CTC. Now, if we were to compare the previous job changes to the current CTC using the same LM flows, we can see from this chart, let me run this. We can see from this chart that there is not much relationship, there is not much correlation between the previous job change and the current CTC. There is not much correlation at all. Correlation values, if not admissible, zero between there's no much relationship, linear relationship between the previous job changes and the current CTC. Then I now let's try using the months, experience in months and the current CTC value. And when we run this, we can see from our regression line that there is also a positive correlation between the experience in months and the current CTC. That is, as the experience of the staff as their experience in months increases, their CTC value also increases. So we now try the graduation marks and try and see the linear relationship between the graduation marks and the current CTC. And from this chart, we can see that there is a somewhat negative correlation, because as the graduation marks is increasing, it's almost like as if the CTC value is decreasing. So that's about comparing or seeing the relationship, the correlation, and the distribution of the various variables in comparison with the CTC variable. We will now go to our next task. The next task, and to do that, first of all, we would have to import the test data set. The next task being to apply linear regression to predict our new CTC. We'll then we'll need to import the test data set. So I will run this and then run our test, import our test data set. And this is our test data set. From this data set, we can see that there are so many issues with it. First of all, we have columns that are unnamed, then so many non-values. So we will need to clean this data set before we can do anything. So the first thing we will do is to remove the unnamed column. And in order to remove the unnamed column, we'll be using the strip method to remove. So what I did here was use this is the test data set, but to locate in the test data set column anything that contains unnamed and strip it. That's the meaning of this statement. Strip any column with the name unnamed. So let's run this. Then when we find out the head, use the head method to find out the data set, we can see that all the unnamed columns have been stripped off. Another thing that we can notice from here is that our predicted CTC is empty, so we don't need it for now. So we would also strip it. We use the same strip method and strip it from the data set. And now we have our data set complete without any none or missing value. We will also try and convert our actual CTC data type to the same data type with our previous CTC using the numpy int, using the apply method on the numpy int integer 64. And as you can see, after I've run that, the actual CTC and the previous CTC are both carrying the same data type. We'll now get the general information. Let's see what our data set, our test data set looks like. We'll use the head function. From the head function, we have the first 5 rows. We use the tail function to get the tail method to get the bottom 5 rows. We get the shape of our test data set, which is, as you can see, using the shape method. And based on these figures, we have 11338 rows and 12 columns. We will get the test data info. These are the columns. You can see we don't have any null value, and these are the various data types of the test data set. Then we get the description. We want to describe our test data set. We want to know the statistics, the count, the mean, the standard deviation, the linear, the minimum value, quartiles, and the maximum value. And these are all the statistics. Now, in order to begin our linear regression, to apply our linear regression, we need to import the necessary libraries from sklearn. And as you can see, because we are having to do linear regression, we'll import the linear model. We'll assign the linear model of linear regression to the regression variable. We will import processing preprocessing from sklearn preprocessing. We will import the standard scalar. We will assign scalar. We will assign the standard scalar to the scalar variable. We will import model selection, import cross value score and we will import R2 score. So let me run this. We have run that. The next thing we'll go to is to train our model. So we're using an extreme variable. In the extreme variable, we'll be using the train data. And these are the variables from the training data set that we will be using to train our model. The experience in months, previous CTC, and graduation mark. In the X data set, we have the test data, experience, previous CTC, and graduation mark. These are the variables from the test data that we're using to test our model. Then we will assign the fit. We will use the fit method, fit underscore transform method, scalar.fit underscore transform method, and we're assigning it to the X train. Scalar.fit transform X test, we're assigning to the X test variable. The Y train data. For the Y train, we're using the CTC value of the train data, and for the Y test, we're using the actual CTC value for the test data. Then we fit our model. In order to fit our model, we use the regression.fit method, and in the regression.fit method, we are adding enclosing the X train and the Y train variables. In our fit method, we also need to find our coefficients and intercept, because this is we are doing this fitting because we want to. This is how we want our regression line. That's the reason why we're doing this coefficient and intercept. And we are fitting, and we want a linear regression chart. And the coefficient and intercept will give us the right chart. So I'll run this. I didn't run this. So I will run this, and these are our coefficient values, and this is our intercept values. Then we predict our CTC. In order to predict our CTC, we would use the predict method. We are assigning the X test to the predict method, and we are assigning this whole factor, we are assigning to the Y test predict variable. We'll also try and build a data frame. We'll create a data frame that consists of the actual CTC and the predicted CTC. The actual CTC being the column name assigned for Y test, and predicted CTC being the column name assigned for the Y test predict. And all of them will be indexed under a predicted value variable. Then we print our predicted value. When we run this, we can see that our actual CTC is this, and this our predicted CTC from our model. This is what our model predicted as the CTC, and this is the actual CTC. This is 71406. Our model predicted 70529. This is 68005, and our model predicted 71122. You can see that there is slight difference between the actual CTC and the CTC that was predicted by our model. Then we will go to model evaluation. Under model evaluation, we want to evaluate the efficacy and the validity of our model. And then we will use the mean squared error. The mean squared error shows the measure of amount of variance in the mean square measure. The mean square error is used to measure how close the regression line is to the data point. How close our regression line is to the data point. And in order to do that, we will use the numpy.mean method. We would remove, we are going to subtract our y-test predict, which is this, from our y-test, and then we are timesing it in double places. Then after we have done that, using this formula, we would print, we want to know our residual sum of squares. Residual sum of squares is used to measure the difference between the observed values and the predicted values. So we want to know the difference between the observed values and the predicted values. We would also find out our root mean square. Our root mean square being this year we are finding out our root mean square because we want to know how well the regression model, the linear regression model, we want to know how well it's doing, how well it fits, how well did our model fit with the test data set, how well did our model fit with our data set. That's why we're doing the root mean square. That's what we're trying to find out the root mean square error. We'll also find out the variance score. Now the variance score shows how far values are spread from the mean. So we want to know how far the values are spread from the mean. So from this mean residual sum of mean square, we will be using the mean square error. For the root mean square error, we'll be using the numpy the square root of the mean square error again. For the variance score, we'll be using the regression score, and we are assigning the x test and y test to the regression score. And in order to, we also want to determine our R2 value. R2 value, and for that we'll be using the y test, and the y test predicts variables. The R2 or the R2 score, the reason why we're finding it is because we want to use it to know the efficacy of, or the validity, or the efficacy or the validity of our trained model. So all this, then another thing we will do is that we will now plot a dist plot. This plot means we want to plot a linear regression plot of the actual CTC against and the predicted CTC. And so we will do that using the y-test predict variable for the actual CTC and the y-test underscore. So you will use the y-test variable for the actual CTC, and then we use the y-test predict variable for the predicted CTC. Then plot our legend because there are two different ways and we want both of them to show. We assigned different colors because we wanted them to show on. I wanted them to show under different colors, and that is the add our show function because we want our chart to show. We also plot a regression plot, an SNS regression plot showing. So this SNS disk plot will show the distribution of the actual CTC and the predicted CTC variable. That's what this SNS disk plot will do. It will show the distribution of the actual CTC and the predicted CTC. Now, the SNS regression plot We will now show the linear regression between the actual CTC and the predicted CTC. So we will run this. And from here you can see that the residual sum of squares is about 134,275,977. It's quite high. Our root mean square is high, 11,587. Our variance score is 0.15, it's a bit low, and our R2 is 0.14, which is also quite low. So we might need to do more evaluation on model evaluation. We might need to change our model because these figures are a bit high and a bit low. So after that, we will now look at, since we plotted a disk plot, this is the chart showing the disk plot with the actual CTC at the x-axis and the density on the y-axis. The actual CTC is represented by the red line and the predicted CTC is represented by the blue line. And from this, we can see that our actual CTC, although the density is not that high, but it's more spread. It had a more spread distribution when compared with our predicted CTC. Our actual CTC ranges from the value of about 4,002 or thereabout to more than 12,000 CTC. But our predicted CTC was more within the range of, let's say, about 6,000 to about 10,000 or thereabout. So the predicted CTC did not have that much spread. It was just centralized between this range, that's 6,000 to about 10,000 CTC values. So then we will now look at based on our code that we we said we wanted to plot the wedge plot chart. And this is the linear regression showing the actual CTC and the predicted CTC. From here you can see the actual CTC on the x-axis, the predicted CTC is on the y-axis. And from this chart, we can see that as our CTC, actual CTC is increasing, the predicted CTC is increasing. But the highest figure for the predicted CTC is about 9,000. No, sorry, not 9,000. About, yes, 9,000. That's the highest value for the predicted CTC, and that's for the actual CTC. That is the current CTC. The highest value was 12,000. So this is what the model produced. So we also test our model using the mean absolute error. And the mean absolute error is so that we are trying to and also validate, we're trying to use different methods to validate the efficacy of our model. That's why I tried the mean absolute error as the second option. So we would import it from the sklearn matrix, and then when we run this is our mean absolute error. These are error values about 8,861 with other figures at the end. So it's quite high. But in order to at least test the validity of this thing, we will compare this mean absolute error with our standard deviation, because this mean absolute error must not be greater than our standard deviation. So when we run this code, test.data.describe actual CTC, we get the statistics for the actual CTC. And from here we can see our standard deviation is about 12,551. And our mean absolute error value was 8,861. So we can say that our model validity our model has as a bit of validity. because at least the error is not higher than the standard deviation. So after this, I think this is the last question under the project assigned, under the project task. This is the last question. So next thing I did was to add the predicted CTC back to the test data set, because we removed it the other time because it was empty. So we removed it. So now that we have been able to use our model to predict the CTC for the new hires, we add it to the test data set. And I use the concat method to enclose the test data set, and then you add the y test predict as a column in the test data set on axis 1. This is what I did here, and I assigned this whole code to the final output, to a variable called final output. And when you run it, you can see that we now have a complete table with our predicted CTC as a column under the test data set. And we import our newly formed Excel dataset. We import it as Excel. I imported mine as new dataset. I named it dataset with predicted CTC. And then I ran, as you can see, I just ran the code. And it tells me that dataset has exported to Excel file. The reason why we are doing this is because we will need to try other methods for testing, for modeling. We need to try other modeling methods on our data set, and it will not. So instead of us having to go through the whole cleaning process again, now that I've moved this, I've saved this new data set, I can continue working on it on other types of models. So I would like to thank you all for listening to my explanations. I would also like to thank the Start Tech Academy for the internship opportunity. I'd like to thank them for providing an enabling environment for easy learning. And I hope you guys find this video engaging. If you have any questions, or if there are any additional things that you'd like to add, you can post it on the comment section. Thank you all, and have a blessed day.